In the previous several lectures, we discussed the concept of inductance and inductors. So we said that when a changing electric current flows through the loops of our inductor, it creates a changing magnetic flux inside those loops. And by Faraday's law, that changing magnetic flux induces an EMF inside our inductor. And by Lenz's law, that EMF will oppose the change in magnetic flux. So in the same way that we can place capacitors and resistors into an electric circuit, we can also place our inductors and resistors into an electric circuit. So because an inductor consists of a wire, and because wires carry resistance, that implies that inductors, as with any wire, carries at least some amount of resistance. So circuits that contain resistors and inductors are known as LR circuits. So let's suppose we have the following electric circuit in which we have an inductor which has an inductance given by L and a resistor which has a resistance given by R. Now this resistance R symbolizes the total resistance found inside our electric wire, and that includes the resistance found on our inductor. Now in this case, because we have no battery source, that basically means we don't have any voltage difference within our electric circuit, and so electric current will not flow. However, at the moment we insert a battery into our electric circuit, current will begin to flow. So if we take a battery and place it into our electric circuit and the voltage on that battery is given by V0, our electric current will begin to flow from the high potential electrode to the low potential electrode of our battery in the following direction as shown by these arrows. Now, what we want to examine in this lecture is the following question. Can we describe the rate of change of our electric current mathematically once we actually place our battery into our electric LR circuit? So let's begin by applying Kirchhoff's second rule. So Kirchhoff's second rule basically states that the sum of the voltage differences across any loop within our circuit is always equal to 0. So let's begin with point 3. So let's suppose our electric current is found at point 3. Now at this point, we define our voltage to be 0. Now when our electric current flows from point 3 through this battery to point 1, it essentially gains a quantity of voltage given by V0, and that is expressed in this form. Now, when our electric current flows from point 1 to point 2, it loses voltage. The voltage drops as a result of this resistor, and that means we subtract negative I times R. Now, finally, when our electric current flows from position 2 to position 3, there's once again a drop in voltage, and the quantity of drop is equal to the quantity of EMF induced inside our inductor, and that is given by the following symbol. Now, in a previous lecture in our discussion on inductance, we said that the quantity of EMF induced is equal to the product of the inductance L and the rate of change of our electric current di dt. Now, by Kirchhoff's second rule, this sum of voltage drops and gains is always equal to 0. So let's express this equation up here. So V0 minus IR minus L di dt is equal to 0, where our I is simply our electric current inside the circuit at some time instant. Now let's take this equation, rearrange it, and we get the following result. So notice that this is a linear differential equation. So if we take this equation and rearrange it into the following form, so we bring the di's and the i's to one side and the dt to the other side. We can take this linear differential equation and integrate it. So let's integrate the left side of our linear differential equation equation from I equaling 0 to I, and we integrate the right side from time equals 0 to some time t. So if we evaluate this side of our integral, we get the following result. So because we have 1 over v naught minus IR, this becomes natural log of v naught minus IR, and then we apply our chain rule and we get -1 divided by R. Now we're evaluating from 0 to I. If we integrate the right side, we simply get t divided by L from 0 to t. So if we actually evaluate these integrals, we get the following result. So negative ln v naught minus IR plus natural log of v naught divided by R. And this side simply becomes t divided by L. So now if we apply the laws of logs, we get the following result. So we combine these and we get this result. Now there's a negative sign here and we have the R on the bottom. So we can bring that to the right side and the right side becomes negative R times t divided by L. Finally, we can take the exponential of both sides. Now, if we take the exponential of our natural log, the natural log simply disappears and we get this fraction inside. And that is equal to our exponent e raised to the power of negative RT divided by L. Now, if we essentially solve for our I, we see that I is equal to V naught divided by R multiplied by 1 minus E to the power of negative T divided by tau, where tau is simply our time constant. It's given by the ratio of L, our inductance, divided by R, our resistance. Now recall that tau simply gives us the quantity of time that it takes our electric current to reach 63% of its maximum value. So, if we take this equation and we plot it on the xy plane as shown, where the x-axis is the time and the y-axis is our current, we see the following curve. So this curve essentially represents the rate of change of our electric current. So once we place our battery inside our electric circuit, our electric current will begin to increase according to the following curve. So this curve represents the growth of our electric current inside our LR circuit once we place our battery with the voltage given by V naught in to our electric circuit. Now we see at time of infinity, at an infinitely large time, our I is a maximum value equaling V naught divided by R, and that's given by this line here. So this line represents the maximum possible value that can be reached inside our electric circuit, and it's given by this equation where V naught is our voltage on the battery and R is the resistance found on our resistor, which includes the resistance of our inductor.